Good afternoon. My name is Jennifer Lowe, and I work at Sandia National Laboratories in the Center for Computing Research. This is a recording of a talk that I previously gave in our summer intern summer series called An Introduction to Trilinos. This talk is meant to be an introduction to Trilinos for the complete beginner who has never used Trilinos before. If you need more information, I encourage you to visit the website for Sandia's Center for Computing Research at ccr.sandia.gov or for the Trilinos project at trilinos.github.io. I hope you enjoy the presentation. Trilinos. Trilinos is an open source library of software for scientific computing. Its purpose is to enable technologies within an object-oriented software framework for the solution of large-scale, complex, multi-physics, engineering, and scientific problems on new and emerging high-performance computing architectures. Below are pictures of two supercomputers, Summit and Sierra, currently ranked number 2 and 3 on the top 500 list of top supercomputers in the world, and Trilinos has been used to run real-life applications on both of these supercomputers. The main GitHub page can be found at github.com/Trilinos. When you go to the GitHub page, you will see the main code base for Trilinos, which you can download. The default branch of the Trilinos GitHub is always on master, and we do development on the Trilinos development branch. If you want to download the source code for Trilinos, you can do so by clicking the green code button. And if you scroll to the bottom of the page, you can find a README with Trilinos instructions and instructions for documentation. Trilinos is made up of several packages, little independent software units within the whole of the Trilinos framework. Currently, there are 57 autonomous packages within Trilinos. They include Kokkos kernels, IFPAC, and Mulu. Each of these packages is self-contained and has its own set of requirements. Each package has its own development team and its own set of users. Some packages are independent and standalone, such as the Kokkos package. Other packages have dependencies on other Trilinos packages, such as tpetra. Each package comes with a unique set of capabilities and documentation and coding styles. If you download the Trilinos source code and go into your Trilinos directory and the packages directory, each package has its own directory within the packages directory of Trilinos. If you want to look at individual package descriptions, you can see more at the Trilinos IO page. Trilinos organization includes 5 main product areas plus leadership. The product lead for Trilinos is Mike Haru from Sandia National Labs. The 5 product areas include data services, linear and eigensolvers, nonlinear solvers, discretizations, and the framework used for documentation and testing. Furthermore, we have product management and interface to Sandia's stakeholder interests. Individual packages within each product area still have their own package leads. And you can see the website for further details if you want to know more about these product areas. In spite of having all of these packages, Trilinos is unified under a single framework. The majority of the code is in C++ with frequent use of templates. There's one GitHub repository, one build configuration system, unified issue handling through the GitHub issues interface, unified testing of all of the packages, and continuous integration. And there are broad guidelines that all packages in Trilinos must follow. Trilinos has been in production for over 20 years, and here are just a few of the many, many sponsors that have helped make this stable and useful software possible. One of Trilinos's big goals is to provide portable parallel code for high performance computing for HPC. Trilinos is targeted for all major parallel architectures, including those current, such as Summit and Sierra you saw on the previous slides, and upcoming architectures shown here, such as Aurora, El Capitan, Perlmutter, and Frontier. Trilinos can be used with high-performance computing, with multi-core processors, and with accelerators such as GPUs. Trilinos provides a structure of software needed by science and engineering applications. At the base, we have Kokkos and Kokkos kernels, along with MPI for parallel communication. On top of that layer sits distributed linear algebra, linear solvers, preconditioners, nonlinear solvers, discretizations, and application codes. We'll talk through each of these layers. But first, let's talk about 3 different application codes which actually use Trilinos. One such application code is ExaWind, which does wind turbine modeling. Another is called Zeiss, which does circuit simulation. And another is called Albany, which does ice sheet modeling. Note that these are codes which use Trilinos, but they are not part of the Trilinos software stack. They are independent codes on their own, which rely on Trilinos for mathematical operations. Starting with ExaWind. ExaWind does wind turbine modeling. It has the goal of simulating the physics of entire wind power plants. This is used to improve wind turbine structures and plant structures to advance the performance of our renewable energy created by wind turbines. ExaWind includes 2 physics-based codes. One is NALU Wind, which does fluid dynamics, the motion of air and water. And one is OpenFast, which studies the turbine dynamics. The NALU Wind code uses Trilinos underneath. And you can read more about ExaWind in the paper below. Zeiss is a circuit simulation software that's developed at Sandia. Its purpose is to verify the design of electrical components prior to manufacture and deployment. Zeiss, in particular, does analog time domain and frequency domain parallel circuit simulation. Its application at Sandia is to predict the reliability of weapon system components when exposed to hostile radiation and electromagnetic environments. In particular, it can simulate the effects of ionizing radiation in transistors and circuits. This is important because such levels of radiation could cause the circuit to become unpowered and quit working. Albany Land Ice Code does ice sheet modeling. The modeling of ice sheet dynamics is essential for providing us estimates of sea level rise towards the understanding of the local and global effects of climate change. Albany implements an open source C++ parallel multiphysics finite element code for modeling these ice sheets. Albany Land Ice provides a scalable land ice solver based on a first order Stokes model. Okay, so those were great applications, but how do these physics applications actually use Trilinos? Let's talk first about discretizations. What is a discretization? A discretization is a way to go from a continuous or infinite dimensional partial differential equation, or PDE, to a discrete set of finite dimensional equations that our computers can work with. Possible methods of discretization are shown in the pictures on this slide. They include the finite element method, as in the picture below, the finite volume method, and the finite differences method. In Trilinos, we have packages that provide discretizations. Discretizations of integral and differential equations. For local or on a single compute node finite element discretization, we use Intrepid 2. For global finite elements, we have the package Panzer, which provides the local to global mappings of the finite elements from Intrepid. For automatic differentiation, we have a package called Staccato, and you can see the video below to explain what automatic differentiation is. And for more building tools, we have a package called phalanx, which decomposes problems into simpler pieces and manages those dependencies between different problems and packages. Moving on to nonlinear solvers and friends. We have continuation algorithms and bifurcation algorithms, which help scientists and engineers to choose which regions of their parameter space are important. In other words, they can use these algorithms to pick which sets of parameters in my equations are most important to study, which ones have different behavior from other sets of parameters. We use these nonlinear solvers to solve nonlinear PDEs, examples of which are here. We have optimization algorithms. So when you think optimization, think of your calculus 1 class where we were trying to find the minimum or the maximum of a certain equation. This is the same thing, just in larger dimensions. We have optimization algorithms for finding minimums or maximums for real life problems. And furthermore, we have time integration solvers. Now, which packages contain these operations in Trilinos? For continuation and bifurcation algorithms, we have LOCA, which is called the Library of Continuation Algorithms. For nonlinear solvers, we have a package called Knox. And if you want to look in the details of Knox, I recommend looking at the Nonlinear Solver Factory. For optimization, we have RAL, which is the Rapid Optimization Library. And for time integration, we have Tempus. And if you want to learn more about what is time integration, I suggest the YouTube video linked below. Finally, underneath the nonlinear solvers and other top-level algorithms, we have preconditioners, linear solvers, which both sit on top of distributed linear algebra. Now, before I go into explaining these preconditioners and linear solvers, I need to take a step back and explain the mathematics behind all of these nested solvers and how these pieces work together. You see, whenever we have a physics problem, which is represented from a partial differential equation, and then we use our discretizations package to discretize it, we typically end up with a set of nonlinear equations. All of the steps in a nonlinear solver trying to solve that nonlinear equation, each step leads to a linear system. AX equals B from your basic linear algebra class, as shown below. The thing is, in real life operations, these linear systems can come to be millions and millions of unknowns, which need to be solved by a large computer. Now, solving linear systems on a large computer is a little bit different than what you actually learned in your linear algebra class. We can't use Gaussian elimination because it takes too much storage on the computer. So what we use are called iterative methods. And to help iterative methods converge to the right solution, we need to use preconditioners with our linear systems. So what you do for a preconditioner is you take your linear system, AX equals B. Remember your basic algebra rule that if we multiply on both sides of the equation by the same matrix, both sides of the equation are still equal. So we pick a matrix M that's called a preconditioner. We multiply on both sides of the equation to get MAX equals MB. And in that case, MAX equals MB, the preconditioned problem, should be easier to solve than the original linear system. And our iterative solvers on our large computers can actually converge to the right solution in a reasonable amount of time. Now, after we have these linear systems and preconditioners, we need a code system for distributed parallel linear algebra for running these solvers on our large computers. So now that you understand that nested layer, let's talk a little bit about sparse linear solvers available in Trilinos. Trilinos contains both direct sparse solvers and iterative sparse solvers. Again, sparse linear solvers are solving a system AX equals B. When I'm saying that the system is sparse, what I mean is that the matrix A contains mostly zeros. I personally do my research in sparse linear solvers and what's called numerical linear algebra. And I have worked with many a matrix where the number of non-zero elements in the matrix is less than 1% of the total number of elements in the matrix. Sparse means they're mostly zeros. We just said that. Here's a quick example of what a sparse matrix might look like. The colored elements are non-zero elements and everything else in the matrix is a zero. First, we have direct solvers. These are similar to the Gaussian elimination you learned in your undergraduate linear algebra class, but we use a few extra tricks to keep the matrix sparse. Otherwise, we'll have lots of fill in, and a lot of those 0 elements will turn to non-zero elements and eat up our computer memory. So direct sparse solvers use a special factorization of our sparse matrix to find an exact solution to our system. In Trilinos, these direct sparse solvers are provided by the package Amesos2, which actually interfaces to a handful of other packages that provide standard sparse direct solver libraries, such as SuperLU and MUMPS. Iterative solvers, on the other hand, choose an approximate solution out of an appropriate subspace, usually a Krylov subspace. Belos, the linear solvers library, works with templated Krylov solvers. It includes the conjugate gradient method, MenRes, GMRes, BiCGStab, or for sequences of linear systems, we have GCRODR. I personally work with development of the Belos linear solvers library, and I would be happy to consult with applications codes on which solver would be best for your application and what settings to use. Belos also provides a simple interface for matrix-free operators. That is, if your linear operator A is stored as a function, an abstract function, rather than actually storing all of the matrix elements, the Belos linear solvers library provides a really straightforward interface for using that type of linear algebra. And we provide block solvers for multiple right-hand sides. Let's move on to preconditioners. Trilinos provides a handful of different preconditioning libraries. Remember that with preconditioning, your linear system AX equals B becomes MAX equals MB, and this matrix M is called the preconditioner, and it makes the linear system easier to solve. M approximates A inverse in some sense, but it isn't exactly A inverse. One type of preconditioners we provide in Trilinos is called multigrid preconditioners. These happen in the MuLu package. It provides our multigrid framework. And you can see in the picture below from the MuLu tutorials manual, approximately what goes on with a multigrid preconditioner. So a multigrid divides your problem discretization into a set of coarse grids and fine grids. It works some on the coarse grids and some on the fine grids, and uses projections to use the information from different solutions to accelerate the different solutions on other grids in the solution of the whole problem. We also provide one-level domain decomposition preconditioners and solvers in the IFPAC2 package. Those include incomplete LU factorizations, Chebyshev polynomial iteration, and relaxation methods, such as the traditional Jacobi and Gauss-Seidel iterations. Finally, we have scalable multiple level domain decomposition solvers, and these are on-node and multi-threaded, provided by the Shilu package. If you're just starting out with Shilu, I recommend looking at Shilu Frosh. Moving on to distributed parallel linear algebra. What do I mean by distributed parallel linear algebra? Well, think, when we're doing linear algebra on large computers, and we've divided up a linear algebra problem into different parallel processors, someone has to decide which processor gets which piece of the problem. How are processors going to talk to each other? So you can see in the diagrams below an example of how a small problem divided up between 4 processors might compute a dot product. Each processor has its own piece, and they have to talk to each other to combine all the pieces. Similar things happen down at the bottom, where we're computing a sparse matrix vector product with a matrix and a vector that are distributed among processors. So in Trilinos, we have the T-Petra library, which provides this distributed parallel linear algebra and helps to decide how these different processors talk to each other and how we divide up our matrices among the processors. T-Petra underneath uses Kokkos for the on-node linear algebra, and MPI, the standard message passing interface, to help processors communicate with each other. A handful of important constructs from T-Petra that you might want to know about include the CRS matrix, the compressed sparse row matrix, which is a standard format for storing sparse matrices without storing all of the zeros. The map tells different processors where are my pieces of the matrix in relation to the whole matrix. That's our local to global mapping. Which pieces do I have, my part of the matrix versus the matrix as a whole? We have a multi-vector, which is just as it sounds. It's an object-oriented construct that can hold multiple vectors and perform mathematical operations with that. And if you happen to be working with matrix market test matrices, we have a matrix market reader and writer. If you're interested in tPetra tutorials, I suggest that you consult the webpage below, and they have some great introductions. A side note about ePetra, ePetra was a package that provided parallel linear algebra before tPetra. ePetra is currently being phased out because it only provides MPI and OpenMP parallel linear algebra. tPetra, on the other hand, since it has a Kokkos layer underneath, works on GPUs and other new modern accelerators. Speaking of Kokkos, underneath everything with our linear solvers and tPetra, we have the whole Kokkos ecosystem. This consists of Kokkos and Kokkos kernels and related constructs. You can see the diagram below. We have Kokkos kernels, which provides on-node linear algebra kernels, such as matrix multiply, matrix vector multiply, these dense operations, triangular solves, and so on, that you need to do linear algebra with a big problem. And the Kokkos core provides even smaller on-node parallel constructs. How do we store a vector of elements? How do we lay out that vector in memory? Kokkos remote spaces looks at PGAS spaces and other constructs. Kokkos support has an excellent set of documentation and tutorials and boot camps. And Kokkos tools provides tools for debugging, profiling, and tuning of Kokkos performance. Kokkos ports to many different CPU and GPU architectures, from multi-core CPUs to just your standard laptop to other high-performance structures. Provides portable parallel linear algebra on a single node. It provides BLAS and LAPACK routines in Kokkos kernels. If you aren't familiar with those terms, BLAS is the basic linear algebra subroutines. It's a standard for general linear algebra subroutines, and LAPACK, the linear algebra package, is a similar construct. And it enables computations on CPUs, GPUs, including NVIDIA, AMD, and more. If you want to learn more about Kokkos kernels, I strongly recommend the excellent lecture series linked below. Remember that Kokkos and Kokkos kernels can be used independently of the rest of the Trilinos ecosystem. So they're both packages within Trilinos and standalone packages. If you want to get started with Kokkos and Kokkos kernels, the lecture series below is excellent. It will walk you from square one, the very basics of Kokkos, to expert topics, and they have a really good set of videos there. Finally, if you're using Trilinos, you should be at least somewhat familiar with common tools available to all users in our library. The Trilinos tool package is called Tephos. That's right. In spite of the spelling, I did say Tephos. It's a FA Greek name that means tools. Tephos provided dense linear algebra before Kokkos. It does have an LAPACK interface. Again, this is something that may be phased out in future Trilinos implementations. Common constructs from Tephos that are important to know include the parameter list construct, reference counted pointers, RCPs. And if you want to know more about that notation, I highly recommend looking up the Tephos RCP Beginner's Guide. It'll explain all the pieces for you. We have certain scalar traits properties for all of the different scalar types that Trilinos is templated on. For example, Belos is a templated linear solvers library. So I can run my linear solver in double precision or in float precision. And these scalar traits and magnitude types provide constructs such as, where is machine epsilon for this current scalar type that I'm using? Tephos also provides timers for timing your code. Finally, we have libraries for graph partitioning, load balancing, meshing, and coloring. These capabilities are provided by the Zoltan 2 library. What is partitioning and load balancing? This partitioning problem is basically answering the question, how do we divide a problem among parallel processors? So once you decided how you want to divide your problem among processors, tpetra will take care of all of the storage and of coordinating the processors one between another. But you can use these partitioning packages to perhaps come up with more intelligent ways to divide up your matrix between processors, as you can see in the matrix problem below. Meshing turns 3D physical objects into 2D pieces that we can work with easier on our computers and with our partial differential equations. Coloring is a method of labeling nodes on graphs. And all of these, again, are provided in the package called Zoltan2. Going back to our applications, how do our applications use Trilinos? I'll quickly brush through this, but Exawind, for example, uses tpetra, Kokkos kernels, Belos, ifpac2, Amesos2, Mulu, Zoltan2, xpetra, I don't think I mentioned that one, it's a linear algebra interface, and STK, which is another meshing package. Similarly, Zeiss uses Zoltan and Isopropia. Zeiss actually uses the epetra stack, the older stack, rather than the tpetra stack. It uses Tefos, Shilu, Belos, Knox, Loka, and other packages. And finally, the Albany ice sheet application package uses Zoltan2 for partitioning, Amesos2 for preconditioners, Mulu and Frosch for preconditioners, Kokkos, tpetra, Staccato for automatic differentiation, Phalanx, Belos, Knox, Intrepid2, RAL, and others. And Trilinos supports many more applications than just these three. Trilinos supports Spark, the Sandia parallel aerodynamics and reentry code. It supports E3SM, which has environmental systems modeling, Aleph, which has electrostatic fields and low density plasma processes, Empire, electromagnetic plasma simulations in realistic environments, Sierra, which studies thermal, fluid, aerodynamics, solid mechanics, and structural dynamics, Ramses, which has radiation analysis modeling and simulation of electrical systems, Charon, which is a semiconductor device modeling code, Allegra, which simulates large deformations and strong shock physics, including solid dynamics, as well as magnetics, magnetohydrodynamics, and electromechanics, and more. So what if I'm a beginner and I want to start using Trilinos right now? The place you start is to go back to slide 3 and download the code from GitHub as per the instructions. And then, if you want to build Trilinos, you have essentially two options to pick from. The first option would be to use SPAC, which is basically a huge all-in-one package manager. And you can start at that link with a tutorial on how to use SPAC. If you want to build Trilinos from source, which is absolutely necessary if you intend to do any development work in Trilinos, you're going to need to download the code from github.com, and then you need to follow the build instructions using CMake and Tribits. You can see quick build instructions at the link in the second bullet below. And if you're not familiar with CMake, I highly recommend the good CMake tutorial below on Udemy. As far as finding resources and documentation for Trilinos when you're getting started, one of the best ways to get started with Trilinos is to start looking at tests and examples for a specific package. Then you can start altering certain parameters in the tests or adding your own construct around it. But I highly recommend starting with an actual example code. How do I find these example codes? Unfortunately, they can be a little bit hard to find on the internet. What you would need to do is go to your Trilinos download directory, go to Trilinos packages, and then choose the directory of the package that you want to work with. Within that package directory, there should be directories labeled example or test, and you can skim the different names of the examples and tests, look at the source code directly, and start with figuring out how to manipulate that source code. If you want information on specific packages, many packages have their own pages on the trilinos.github.io pages, which give good information. And then those pages have links to the Doxygen documentation. Furthermore, you can see the link below for Trilinos tutorials. It's really a conglomeration of tutorials for a handful of packages. A little word on Doxygen pages. Not every package uses Doxygen for documentation, but where they do exist, they're very useful to see the code API. So for example, here's a screenshot of a Doxygen page for the Balos Block GMRes Solver Manager. At the top here, I can see the inheritance structure of all of the objects around the Block GMRes Solver Manager. I can see the constructor calls and the destructor calls and different accessor methods, and it goes on through all the methods available in that Block GMRes Solver Manager class. Similar things here, I can look at the tpetra multivector update function. It tells me that this adds vectors together with certain scalars, tells me which arguments go where, and where the definition is in the source code. Doxygen pages can be very useful. Can I contribute to Trilinos? Absolutely. Trilinos has a broad community. The code for Trilinos is primarily developed at Sandia, but we have contributors all over the world. When I pulled up this information, Trilinos had currently 242 contributors. I think I was number 212. You could be number 243. To find instructions for contributing to Trilinos, see the contributing guidelines at this link. The contributing guidelines give you instructions for making your own fork of Trilinos, working an issue, creating a pull request, and there's further testing and approvals by the Trilinos code members. So if you are from outside the Trilinos organization, you can create a pull request with your suggested change. The pull request will go through automated testing. The pull request will need review from some of our local Trilinos developers. And if it gets approved, it'll be merged into the Trilinos code base. A few items that are new and upcoming in Trilinos. We're currently adding portability to AMD GPUs for the entire Trilinos stack. So this is already available in Kokkos and Kokkos kernels, but we're working on moving it for all of Trilinos. We have UVM removal in progress for all of Trilinos. UVM is Unified Virtual Memory, which is common on NVIDIA GPUs, but not so common on all GPUs. So that removal is in progress and has been accomplished successfully in several Trilinos packages. And finally, we're working on some mixed precision linear solvers, which are currently under development. Thanks today to all the Trilinos developers and all the work that you've done in making this software a success. And particular thanks to those who helped with preparing this presentation. I hope this was useful for you. Please feel free to look into the resources listed on this presentation if you want to know more. Thank you.